Welcome back to The Explainer. Today, we're diving into a topic that is an absolute must-know, especially if you're tackling your Cambridge IGCSE additional mathematics syllabus. We're going to completely demystify permutations, combinations, and factorials. So often in exam prep, students either overload on raw facts without analysis, or they rush and totally miss what the question is actually asking. Our goal today, to find the back door into every one of these counting problems. We're going to work smarter, not harder. We'll break these concepts down conceptually so that when you see them on a paper or out in the real world, they make perfect logical sense.
Look, if you're staring at those mathematical terms right now and feeling your stress level spike, you are absolutely not alone. Complex math can look like complete gibberish at first glance. But I want you to keep this fantastic quote from Nelson Mandela in mind. It always seems impossible until it is done. It's so true, right? By the end of this explainer, these seemingly impossible concepts are just going to be reliable, everyday tools in your logical toolkit.
To get our brains warmed up, let's look at a puzzle you might actually encounter in the real world. Imagine a combination lock. You've got 4 numbers you need to crack, and 6 choices for each number, let's say digits 1 through 6. If you have zero idea what the code is, but you urgently need to open it, how long would it take you to systematically try every single sequence? How many possibilities are actually sitting right there in your hands? It's a super practical question, and solving it takes the exact mathematical strategies we're mastering today.
Okay, let's dive into this. Here's our clear, logical roadmap for today's session. We've got 4 key steps to cover. First up, unlocking factorials. These are your absolute foundational building blocks. Second, we'll hit permutations, which is all about what happens when the exact sequence of things is critical. Third, we explore combinations, where we only care about selecting a group. And finally, the ultimate showdown, permutations versus combinations, so you never, ever mix them up when the pressure is on.
Let's hit Section 1, Unlocking Factorials. These really are the foundational building blocks of counting possibilities. If you want to grasp anything else today, you have to understand this core concept first. But don't worry, we don't need any abstract, complicated math just yet. We just need to look at a regular, everyday organizing problem. Picture a student named Winnie. She's tidying her bookshelf and has 5 different math books she wants to line up in a row. How many different ways can she arrange them? Let's logic it out step by step. For that very first space on the shelf, she has 5 possible books she could choose, right? Okay, so she places one. Now she only has 4 books left for the second space, then 3 books for the third space, 2 for the fourth, and finally just 1 single book left to squeeze into that last space. To find the total number of arrangements, we just multiply these choices together. 5 times 4 times 3 times 2 times 1. That gives us a grand total of 120 unique arrangements just for 5 books.
And that descending multiplying sequence, that perfectly introduces our first official definition, a factorial. You'll see it written as a number followed by an exclamation point, which we just read out loud as n factorial. It's literally what we just did with Winnie's books. It's the number of ways to arrange n different objects in a line. You calculate it by taking your starting number, n, and multiplying it by every positive integer below it, all the way down to 1. So Winnie's bookshelf problem was simply 5 factorial, or 5i.
Now here is what's genuinely wild about factorials, how explosively fast they grow. We just saw that 5 factorial is a pretty manageable 120. But what if you had 10 items to arrange, say 10 books on a shelf? Well, 10 factorial, 10 times 9 times 8, all the way down to 1, is a staggering 3,628,800. That is over 3.6 million different ways to arrange just 10 items. This rapid, massive growth is exactly why guessing things like passwords or long lock sequences is practically impossible for a human to do quickly.
Before we move to the next step, there is one very special mathematical convention you absolutely must commit to memory. What is 0 factorial? It kind of feels intuitive to just guess 0, right? But mathematically, 0 factorial is defined as exactly 1. It's a vital rule. Without it, the formulas for permutations and combinations we're about to use just wouldn't work. So lock that away in your brain right now. 0 fact equals 1.
All right, let's move to Section 2, Permutations. This is where we calculate possibilities when the sequence is absolutely critical. Now that we have factorials under our belt, we can easily tackle this next idea. This is all about situations where the specific order of your items is the main event. A permutation is often written out as NPR, which simply means arranging R objects from a total of N objects. It is an ordered arrangement. So the absolute crucial takeaway here is order matters.
If you swap the first and second item, boom, it counts as a completely different arrangement. Think about it like a race. Crossing the finish line first is fundamentally different from coming in second, right?
Let's ground this with a real example. A viewer named Joida noticed a cookery competition that had 10 total contestants. She managed to accurately predict the top 3 winners in their exact finishing order. So what were the chances of her actually doing that? Let's break it down. There are 10 possible winners for first place. Once first is locked in, there are 9 people left who could take second place, and then 8 people left for third place. Because the exact ranking of first, second, and third absolutely matters, we multiply 10 by 9 by 8. That gives us 720 different ways those top 3 could have placed. Joida nailed a 1 in 720 permutation. This right here is your classic 10p3 calculation, permuting 3 objects out of 10.
Moving right along to Section 3, Combinations, selecting the group. This is all about finding groups when the order doesn't matter. What happens when we want to form a team or a group, but we suddenly don't care at all who was picked first, second, or third. We just want to know who made the cut. Welcome to the realm of combinations.
A combination is denoted as NCR, choosing R objects from N total objects. It's a selection where order is simply not important. If you pick the numbers 1, 3, and 15, it is considered the exact same group as picking 15, 3, and 1. You're basically just tossing them all into the same bucket. You are solely concerned with which ones are picked, not the sequence they were picked in.
To really grasp how this works, let's look at a practical application. A math teacher plays a game with her class. The students have to pick 6 winning numbers out of a possible 19 numbers. Then, the teacher uses a machine to generate 6 random numbers, and if they match, the student wins. Does it matter what order the machine spits those winning numbers out? Not at all. You just check if your 6 numbers match their 6 numbers. The order is entirely irrelevant.
So, how do we calculate the probability of a student actually winning this game? Let's break down the logic carefully. First, you start by calculating it as if it were a permutation. 19 choices for the first number, 18 for the second, all the way down to 14 for the sixth number. But hold on. If we stop there, we are counting the sequence 1, 2, 3, 4, 5, 6 as completely different from 6, 5, 4, 3, 2, 1. And we know they're the exact same ticket. To fix this, in step 2, we have to divide by the number of ways our 6 chosen numbers can be internally rearranged. And as we learned earlier with Winnie's books, arranging 6 items is just 6 factorial. So we take our permutation and divide it by 6 factorial. The final result? 19 choose 6 gives us roughly 27,000 unique combinations. So, a student has about a 1 in 27,000 chance of winning.
We've made it to our final section, Section 4, Permutations versus Combinations, the ultimate test. Does order matter? It's time to bring everything we've learned together and put these two concepts head to head. The ultimate test whenever you face a counting problem is pausing and asking yourself that one simple question.
This brilliantly illustrates the core difference you need to remember. For permutations, NPR, order strictly matters. Think of it like a race finishing order. Getting the gold medal is fundamentally different from getting the bronze. For combinations, NCR, order does not matter. It's like choosing 5 students to go on a trip to the theater. It makes absolutely no difference if you were the first student called or the 5th student called. You still get the exact same ticket to the theater. Oh, and by the way, fun fact, based on this rule, that combination lock we talked about at the very beginning, it really should be called a permutation lock because the specific order of the numbers is completely critical to popping it open.
Let's cement this with one last clear example. Imagine you need to select a student representative committee of 5 people from a pool of 9 applicants. Since a committee is just a group of equals, there's no president or vice president here, just members, the order we draw the names doesn't matter one bit. Therefore, we use a combination. It's 9 choose 5 or 9C5. When we plug that into our formula, calculating the permutation and then dividing out the 5 factorial redundancies, we find there are exactly 126 different ways to form that specific committee.
We've covered some serious ground today, moving from the explosive, mind-bending growth of factorials to the highly structured logic of permutations and combinations. You've now got the strategy to tackle these problems head-on. So I want to leave you with this final, provocative thought. If these exact principles govern everything from the security of combination locks to your chances in a lottery or a local cookery competition, what daily decisions are you unknowingly leaving up to pure mathematical chance?
Keep your eyes peeled this week. Once you understand the math of possibilities, you start seeing these patterns literally everywhere. Thank you so much for joining me on this explainer, and keep questioning the math behind your world.